All right, so let's continue on the section 4.5, the eigenvalues and the eigenvector. Okay, the eigenvalues and the eigenvectors we're trying to talk about is actually aroused from how we learned about the quadratic form of the square matrix in the previous section. This is very useful. We can characterize some of the special features of the square matrix and could be applied to physical science and engineering. Especially in multivariate statistics, we can decompose the square matrix into the variance and the covariance form. And especially on the principal component analysis and the factor analysis, we can figure out which factor is most effective out of the factor analysis. Okay, so for example, if we have a multi-factor regression model, and imagine that we have the matrix representing all of the coefficients for the multifactors, then we can try to decompose that factor or the matrix factor into the variance and the covariance form associated with a certain value of the eigenvalues, and to find which factor is most effective affecting the model. Okay, so let's look at the steps on how we can find the eigenvalues and the eigenvector. Okay, so sorry, we should start from slide 15. The eigenvalues and the eigenvector, assuming that we have a matrix A, which is a square matrix n by n, then they're associated with a non-zero vector. Let's call it V, and the vector V would have a dimension of n by 1. And that's associated with a constant lambda. In this case, if I multiply the matrix, the square matrix, to the non-zero vector V, that also equals to a constant lambda multiplied to that vector. So in that case, we call that constant lambda, we call that the eigenvalue. And then the vector will equals to the eigenvector. So this is essentially like a linear transformation into the multiple of itself, of the matrix A itself. So the eigenvalue is the, we can call it the characteristics root, and the eigenvector is called the characteristics vector of the matrix A. What does that mean? Let's look at some of the real numbers. For example, we have a square matrix 2 by 2, having 4, 1, 3, 2 of the entries. Assuming that we have a 2 by 1 vector, the content is 1, 1. If I multiply this matrix to that vector, so I'm doing a linear transformation of that matrix to the vector 1, 1. Multiply A, B, putting them together. A 2 by 2 multiply to a 2 by 1 vector, we will have a 2 by 1 vector as a result. Okay, so 4 times 1 plus 1 times 1 would be 5. 3 times 1 plus 2 times 1 would be 5. So look at this resulting vector is 5, 5. And we can take out the common factor 5 in front of this. So that becomes 5 times the vector itself. So in that case, 5 would be the lambda. V would be the eigenvector. Let's look at another case. Let's assume the vector equals to 1 minus 3. We multiply the matrix A to another vector, which is 1 minus 3, doing another linear transformation, and the resulting vector is equals to 1 minus 3. So in this case, 1 minus 3 is also another eigenvector, whereas the constant in front of it, which is a lambda, is 1. So in this case, we can say that the matrix, square matrix A, would have 2 eigenvectors associated with the 2 eigenvalues. We're trying to do a linear transformation of the matrix with the vector, and then it turns it into itself. So under the theorem, for any n by n matrix A, lambda is defined as the eigenvalue of A, if and only if that we can find that the determinant of lambda multiplied to the identity matrix minus the matrix A itself is equal to 0. So let's go back to the matrix A. If I have lambda I minus A, so lambda I is indeed the diagonal entries equals to lambda of diagonal entries at 0. So if I subtract a 2 by 2 by another 2 by 2, so that becomes lambda minus 4, lambda minus 2, 0 minus 1, 0 minus 3. Okay, so let's look at the determinant of this matrix. So that would be lambda minus 4 multiplied to lambda minus 2, subtract the products of minus 1 and minus 3. And I want that equals to 0. Now we have a quadratic forms for the lambda. Lambda squared minus 6 lambda plus 5 equals 0. So we can find the exact lambda's value 1 and 5 that is associated with the matrix. This is the same as we find in the previous slide that lambda 1 is equals to 1, lambda 2 is 5. So when lambda 1 equals to 1, then we're trying to multiply that to a certain vector. Assuming that we don't know what the v would be, we need to find the eigenvalues associated with lambda 1. Okay, so we know that we do a linear transformation of the matrix, or matrix A multiplied to V1 is equals to lambda 1 multiplied to B1. Okay, lambda 1 is just 1, so that becomes A and B. So we can solve for this equation. 4A plus 1B equals to A, 3A plus 2B equals to B, right? So now we have the two equations in the system. We can solve for A and B, and then we find that we can find B equals to minus 3A. In this case, we can put it into the vector is indeed equals to, if I have A constant, A is as itself, so that would be a 1, and then B entry will equals to minus 3A, so we just have a minus 3. So we find the vector that is associated with lambda equals to 1, which is the value of A. So the vector 1 is equals to 1 over minus 3 multiplied to a constant A. We do the same procedures with another eigenvector that is associated with the lambda value 2 equals to 5. So we multiply matrix A, multiply to a certain vector, V2, and equals to 5, which is the lambda 2 multiplied to the vector. So solve for this system, we find that D equals to C. So assuming C is a constant multiplied to the vector 1, 1. So we know that the vector 2, or V2, could be a constant C multiplied to 1, 1. So in this case, we find the multiple of an eigenvector is also an eigenvector. Okay, so now we need to find what are the values of C and what is the value of A. If that's the case, we want to standardize and find the eigenvector with the length of 1. So we need to find the unit eigenvectors. In this case, the definitions, I want to find that AB equals to lambda V. So we can have the constant of multiplying that vector with a constant. So standardizing it is indeed, I need to find the vector that we find equals to 1 minus 3, standardize it by the length of 1, so divided by the square root of the square of both of the entries. In this case, that becomes 1 squared plus 3 squared taking a square root. So we find a standardized eigenvector equals to 1 out of root 10 and minus 3 out of root 10. Okay, so we can do the same for the second eigenvectors. The properties of the eigenvalues and the eigenvectors is that the multiple of an eigenvector is also an eigenvector. So the constant C could be anything. we can have a multiples of the C multiplied to the eigenvectors. But what we need to do is to find the standardized size of the eigenvector. If the matrix has at least one zero eigenvalue, then A matrix is singular. Singular means we cannot find the inverse of the matrix. A and A transpose have the same eigenvalues, but not necessarily have the same eigenvectors. So this is very important that even though we can find the same eigenvectors, the same eigenvalues, we are not always finding the same eigenvectors. Lambda is the eigenvalue for the matrix A, then lambda to the power k would also be the eigenvalues of the multiplication of the matrix A to the power k. Lastly, if lambda is the eigenvalue of A, then the inverse of the lambda is also the eigenvalue of the inverse of the matrix A. And if the matrix A, we can decompose it into the Q inverse multiplied to A multiplied to Q would have the same set of the eigenvalues. So if we find a product of a inverse of the matrix Q, multiply in front of the matrix A, and we have the Q multiplied to behind that, would have the same eigenvalues as the matrix A. Eigenvectors corresponding to the distinct eigenvalues are called the orthogonal matrix. Okay, so when we find that if the eigenvalues, they are distinct, then we try to find the products of the eigenvectors. The products of them would equals to 0. And this is called the orthogonal eigenvectors. We can try to put all of the eigenvectors into a matrix, let's call it P. So for example, if we have n numbers of vectors or the eigenvectors, so we can put them in a column forms and to form this orthogonal matrix. Orthogonal matrix, according to the properties number 7, if we multiplied the transpose of U1 to U2, we should have a 0 values. And assuming that each of the eigenvalues associated with each of the eigenvectors, they are distinct. If that's the case, we can also say that we can look at the transpose of the orthogonal matrix P multiplied to the orthogonal matrix itself. It would end up having the identity matrix, okay? So this is called the orthogonal matrix. By the theorem, combining property 6 and 8, we should find that there's an n by n systematic matrix A with distinct eigenvalues. So each of the eigenvalues, number 1, number 2, up to lambda n, if I multiply the transpose of the orthogonal matrix, which consists of all the eigenvectors, to the matrix itself, and multiply to the orthogonal matrix P, we should end up having D matrix, and with all the entries of the diagonals are the eigenvectors, eigenvalues lambda. And all of the off-diagonal entries, they are equals to 0, okay? So if that's the case, we can decompose our original matrix A into the eigenvectors matrix, multiply to the eigenvalues matrix, and multiply to the inverse, the transpose of the eigenvectors matrix. Okay, so again, I want to say that from the original matrix A, we can decompose or diagonalize it into the eigenvectors matrix multiplied to the eigenvalues matrix and the transpose of the eigenvectors matrix. All right, so let's look at this example. We have a 3 by 3 matrix. We want to find the determinant. First step to find the eigenvalues. we need to find the determinant of the matrix A, which equals to 0. So the determinant of lambda I minus A equals to 0. So we try to look at this and trying to find each of the lambda values, multiplying the formulas of finding the determinant. So we have this lambda minus 3 multiplied to the determinant of this square matrix, plus minus 1 multiplied to the determinant of this matrix, and then plus 1 multiplied to the determinant of this square matrix. Okay, so after all of the procedures, we find the 3 factors of the lambda. Lambda with either equals to 3, 2, and 6. So with the 3 by 3 square matrix, we should be able to find 3 unique eigenvalues. Now the next step is we need to find what are the eigenvectors that is associated with each of the eigenvalues. Let's use lambda 1 equals to 2. So we know that the matrix itself multiplied to the eigenvectors would equals to the lambda multiplied to the eigenvectors A, B, C. So solving the values of A, B, and C, we can have the first eigenvectors which equals to a constant A multiplied to a vector 1, minus 1, and 0. Then we want to standardize this length of this 1, minus 1, and 0 with the length of 1 to find the value of A. So that's all divided by the square root of the summation of the square of each of the entries. So that would be 1 square plus 1 square plus 0 square. So that would be root 2. So we find that the first eigenvector that is associated with the eigenvalues of 2 would be 1 out of root 2 minus 1 out of root 2 and 0. Okay. Then we continue the procedures so that we can find eigenvector 2 that is associated with the eigenvalues 3, eigenvector 3 that is associated with the eigenvalues 6. Now, with that matrix A, we can decompose that into the orthogonal matrix P multiplied to the eigenvalues matrix with all the diagonal entries equals to the eigenvalues and multiply to the transpose of the orthogonal matrix P, right? So first of all, we find P with the orthogonal matrix P that is consists of all the eigenvectors in the columns form. And then the diagonal matrix with the eigenvalues. Okay, so with that diagonalizations or the properties of the decomposing the matrix A, we can look at some additional properties of these diagonalizations. With these determinant equals to the product of the eigenvalues. So with this property, that A equals to P times D times transpose of P, in other words, the determinant of our matrix A would equals to the products of the determinant of the 3 matrices, okay? And then we know that the determinant of P or our orthogonal matrix is indeed equals to 1. And then the determinant of the diagonal matrix D with all of the off-diagonal entries equal to 0 is indeed the products of all the diagonals lambdas. And then the transpose of the orthogonal matrices, the determinant is also equals to 1. So in this case, we find that the determinant of our original matrix A is indeed equals to the products of all the eigenvalues. This could be very useful. Okay, so if I can look at the original matrix A, first of all, we find it pretty complicated to find the determinants of a 3 by 3 matrix. But now, since we can decompose it into the eigenvalues, by that definitions, I know that the determinant of the matrix A is indeed equals to the product of lambda 1, lambda 2, and lambda 3, that equals to 36. The trace equals to the sum of the eigenvalues. So with this, we also want to find the trace of the matrix A. Then that equals to the trace of the compositions. Or we can slightly change the orders of it. So with that, we know that the transpose of P times P is equals to 1. So in this case, the trace of A, which is the summation of all the diagonal entries of the matrix, is indeed equals to the trace of D. And D would have all the values of the lambdas. Okay, so if I just want to find the trace of A, which is the summation of all of the diagonal entries, it's the same as the trace of the summations. The trace of A is the summation of all of the lambdas, which is 2 plus 3 plus 6, same as the summation of 3, 3, 5. Okay, now we want to look at the power matrix A equals to the products of the P times K times of the diagonals, lambdas, and transpose of P. Okay. Now this is very important, that if I want to find the square root of the matrix A, for example, we have the matrix again, A, with this, and then we have the orthogonal matrix P. I know that if I want to find the A to the power K, it's indeed the same as my orthogonal matrix P multiplied to the diagonal matrix with all the lambdas entries to the power K multiplied to the transpose of the orthogonal matrix. Okay, so in this case, I can find the multiply that out with all of the orthogonal matrix multiplied to the diagonal matrix. So I find that A to the power K would have all these entries. If I'm looking for the square root of the matrix A, then with the same theorem, we can say that we can decompose it into the orthogonal matrix P multiplied to the square root of the eigenvalues. Diagonal matrix multiplied to the transpose of P, and then we can find that is the square root of A. Okay, so let's see if we can try to decompose what is the square root of the matrix A. So simply taking the square root of all of the lambda's value and multiply to the orthogonal matrix. So with this multiplications, we can simply multiply that out and then to find out the square root of the matrix A. Okay, so this is one way of finding the square root of the matrix A, and then to find the decompositions of this square root of A. Okay. I hope that you find this is interesting and this is helpful with the matrix decompositions. And that's actually concludes all the materials that I like to review on this preparatory course of the matrices and calculus. Okay, so what I'll do is to upload the exercise for lecture 4, and then after the weekend, I will upload the solution for you to review on. Okay, so hopefully you get yourself prepared to start your master's degree with our department, and I'll see you around. Good luck.